Wonderful.
Yeah.
From the top. I'm delighted to welcome Matteo Cantiello this week for our colloquium. And, as usual, I think that we can all take a moment to reflect with gratitude that Matteo has taken the time to be here, and also that you all have taken this time amidst a challenging winter. I don't know if any of you know, there's like an old carol called "In the Bleak Midwinter," but that's like been on my mind lately. Okay, but back to introducing Matteo. Matteo is a research scientist at the CCA, the Flatiron Institute for Computational Astrophysics in New York City. Before that, he was a postdoc at the Kavli Institute for Theoretical Physics. And one of the roles that he played there was really a crucial role in developing and expanding the MESA stellar evolution software, which has become just an incredible sort of widely used, widely referenced open source software tool for understanding how stars evolve. With that in mind, I guess I wanted to say just very briefly, one thing that I personally really admire about the way that Matteo works is that in the effort to understand how stars are evolving, I've seen Matteo really take a role of like bringing together our field and bringing together expertise on all of the little ingredients that go into this complicated solution of understanding how stars evolve, so that we can improve those parts and eventually improve our prescriptions in sort of a composite simplified model like a 1D stellar evolution code. So Matteo is an expert on all things of how stars evolve, eventually die as massive stars, and give us the sorts of remnants that lead to compact object mergers. And today he's going to talk about the lives of stars in a more gaseous environment than normal, in disks around Aegean. So thank you so much.
Thank you, Morgan. Okay, I'm going to start and share my screen. Let's see if we can get started with this. All right. Okay, so my job today is to tell you a little bit about some work I've been doing recently on stellar evolution in Aegean disk. I want to start straight away saying that I'm very excited about this work, if anything, because it brings in this passion that Morgan was talking about stellar physics, at the crossroad of a number of disciplines that I usually do not intersect with. And so, working with stars in Aegean disk brings in dynamics, brings in the galactic evolution, feedback, accretion processes, and even gravitational wave sources and high energy astrophysics. So I will try to convince you that this is a very interesting topic and something worth thinking about. So first, I want to acknowledge a growing team of colleagues that helped me through last year to develop some of the ideas that I'm going to discuss about. In particular, Alexander Dittman, who is a pre-doc, was a pre-doc at CCA and is a PhD at University of Maryland. Adam Germain, who is a postdoc at CCA. And then my more senior colleagues, Doug Glean at UC Santa Cruz, and Rosalba Perna at CCA in Stony Brook. And this team is growing. I'm talking to more people and interact with other colleagues and developing new ideas. So it's very interesting that, by branching and looking at another region, astrophysical region where stars might form, I also start interacting with colleagues that I didn't interact before. So I find this very, very good for me. So yeah, what is this talk about? Well, the main idea is that stars can be born or even captured by Aegean disks. And because of that, their evolution can be changed substantially. And what we did, we looked at how to modify the numerical problem, the stellar evolution boundary condition, to account for the presence of a gaseous medium of high density around the star, especially in the regions close to supermassive black holes. we found out that the most important processes are bond accretion, internal mixing in the star, and mass loss that occurs when the star becomes very luminous. Because we will see that the stars tend to accrete and become massive and very massive objects. So this has an impact for the production of compact remnants and relativistic explosions. Not only we believe that the presence of the stars might lead to evolution of Aegean composition through the deployment of nuclearly processed elements like heavier than helium into the disk. And also this might have a feedback on the Aegean structure and evolution. So I mentioned Aegean, so active galactic nuclei. What are those? These are like very bright cosmic sources. They're powered by, we believe they're powered by the accretion onto supermassive black holes. Usually, the structure is complicated, but usually discussed very simplistically here as a geometrically thin accretion disk surrounded by a broad line region of emission and a path of torus. And there are models that try to incorporate different pieces of physics to calculate what the gas conditions in this disk are going from in the region outward. This model are fairly complicated. I think they're still in their infancy, but this is possible, and people have ideas on what this condition might be. And this will motivate the condition that we will use to calculate our stellar evolution model of Aegean stars. Important to notice that those disks are not infinitely lived. They actually have finite lives, and the lifetime are of the order of 10 to the 6, 10 to the 8 years. And also interesting and important for this talk, a piece of observation that shows that the inner regions of this disk seem to be enhanced in their composition. So their metallicity seems to be high at all redshift and only increase with the mass of the central black hole. So why do we want to study stars in Aegeans? Well, the idea is that, first of all, Aegeans are actually relatively common. About 1 to 10% of all galaxies go through, or at least are in that phase, are observationally in that phase of evolution. And the immediate surroundings of the supermassive black hole are actually densely populated. Usually we talk about neutral stellar cluster. These are clusters of stars that are living in the neighborhood of the supermassive black hole. If you look at this galactic center around Sagittarius A star, there are about 10 to the 7 stars just within 1 parsec of the supermassive black hole. And obviously, people have mentioned, or people have studied the possibility that stars can form in Aegean disks. So there's also the possibility of having a star form there and evolve in this environment. So as I mentioned, there's one avenue to formation of stars in Aegean disks, but also stars can be captured from the nearby nuclear stellar clusters. This process of stellar capture relies on hydrodynamical drag and the excitation of waves in the disk. So this cartoon is showing a little bit of idea here. We're capturing typical low mass star from a nuclear star cluster. They get embedded into the Aegean disk. And as we'll see, one of the possible outcome is that the density or the accretion rate is high enough, those stars can turn into massive and supermassive star. So, okay, so that stellar physics and stellar evolution in general, it's a fairly successful story of astrophysics from the numerical standpoints. If you look at an HR diagram or a CMD, you can actually map qualitatively pretty well the position of stars. You understand what phase of evolution they're going through. And I will even say that for low mass star, this understanding is quantitatively pretty good. In the era of high precision stellar physics, I also want to make the case that there is still a lot of uncertainties, and this is a part of the work I usually do, especially in massive stars. We're still understanding how basic physical process might affect evolution. But overall, this theory is considered well established. However, canonical stellar evolution is usually assumes the presence of a star in a cold, relatively empty interstellar medium. So the surface boundary condition of the stellar evolution problem account for low external temperatures and vanishing pressures. But the densities in Aegean disks can be much, much higher than your typical run-of-the-mill ISM, up to 10 to the 10 times actually. And the typical sound speed can be on order 10 kilometers per second. So the accretion rate on these stars might be very, very large. So if we want to model these stars, we need to go back to the blackboard and include new ingredients. And we'll see that important ingredients require our new atmospheric boundary condition and a count of accretion onto the star and mass loss. And mass loss will become important because, as you can imagine, as the star accrete and become very massive, will also become very, very luminous. And the stars that we're going to discuss all approach the ending luminosity. So boundary condition, okay. So as you imagine, the star embedded in Aegean disk accreting material from the disk, from this outer Bondi radius, so this is the radius from which material will start falling onto the star, there is going to be an accretion stream produced and a shock over the star. Obviously, you wanna evolve stars for a long time scale, and so you don't want to have to resolve the shock radius above the shock radius. So we're assuming that the outer boundary of the MESA model is at the shock radius, and we will use analytical solution to tell MESA what the condition of the shock boundary are by knowing what the analytical solution for the material falling onto the star are. So to do this, we pretty much derive the structure of the accretion stream, making some assumption and approximation. So we'll assume a spherical symmetry, a steady state. We assume that the stream is not pressure supported and that energy is transported mainly by heat via radiative diffusion. And then the luminosity is constant in the stream. Also, the mass of the stream is small compared to the mass of the star. And then we assume the opacity in the stream is constant and equal to the Eddington scattering level. We check that these assumptions are usually fulfilled, and we discuss in the paper, possible departure of this assumption. But the overall message is, I think, that these are pretty safe, and so they allow us to calculate models of stars in this condition. And so just to familiarize a little bit with this new boundary of the stellar evolution model, so different radii, I'm showing here one of these calculations that I'll also show you later. For now, just notice that as function of time, the mass of the star, the blue line, increases very rapidly to about 200 solar masses. This star started as a 1 solar mass. So this was a sun embedded in an Aegean disk. It grew to 200 solar masses in about 70 million years. So the largest radius of the problem is the Bondi radius, which is always like 10 to 1,000 or 10,000 times bigger than the stellar radius. The shock radius, which corresponds with the radius of the MESA model, is this pink curve. And then there is a photospheric radius that you can imagine you can build by calculating what the opacity, with knowing the opacity, calculating the optical depth into the accretion stream. And you can see that this usually corresponds to the shock radius as long as the accretion is not too large. The accretion rate is not too large, but then as the star accretes at very, very large rates, you start seeing into the accretion stream at larger radii. So in a sense, this is the radius of the star that you will see if you're sitting at the Bondi radius and you're looking down. Okay, so that star that is reaching about 200 solar masses, obviously it's the Eddington limit. And so what's going to happen there? Well, we're going to have accretion onto the star, the Bondi accretion, that is going to be opposed by the tendency of the star to want to lose mass. And this is because the star is close to the Eddington luminosity. In this case, what we do, we assume that accretion is reduced. Obviously, this is a complicated multidimensional problem. But what we do, we reduce the accretion rate as the star gets closer and closer to the Eddington luminosity. We try different ways to do this, and we found out that the solutions are not too sensitive to the way we reduce the accretion. At the same time, we actually losing mass, and the mass loss rate is some typical enhanced super Eddington wind, which is scaling with the extra luminosity turn into a wind. So these are the three main ingredients: atmospheric boundary condition, accretion, and mass loss. The other ingredient that is very important for this star is mixing. So I'm going to make the case now that as they start growing mass, they're going to evolve chemically homogeneously so they stay well mixed. The reason is that, first of all, as stars get massive and very massive and supermassive, their inner region become more and more convective. So a 100 solar mass star has 90% of mass covered by core convection. So the star is already fairly well mixed by the usual convective mixing, but also the other region, the relative region, is getting closer and closer to marginal stability. So gamma equals 4/3. So any type of instability can easily grow in this radiation-dominated region. At the same time, you have accretion and mass loss are interplaying, so you're going to have some kind of circulation that probably are driven by this process. So all in all, we expect the stars, together with the fact that, as we'll see later, the stars probably also rotate rapidly, to stay well mixed. So we implement like an extra diffusivity in the star that allow the star to bring to the surface nuclei processed material as it evolves. And you can see it here in this plot. This is a Kippenham plot, time as function of mass coordinate. And you can see that material here, around 67 solar masses, 67 million years, sorry, is actually dredged out from the core by this extra diffusivity and start making its way into the envelope to the surface. And this is a helium-rich material, as you can see. You can see the diffusion coefficient gets larger and larger as the star gets closer and closer to the azimuthal luminosity. Okay, so with these ingredients, we're able to build MESA stellar evolution calculation. So we implemented this new type of physics into MESA. And then what we did, we took solar mass velocity, one solar mass models, and we embedded into an Aegean with different density and sound speed so that we can regulate the accretion rate onto the star. We assume constant composition of accreted material, and for now we neglect the effect of rotation, although I'll show you later that Adam Germain is working on that piece of physics as of now. So this is showing the evolution of one of these stars. This is a Kippenham diagram again. This is a log of time from the beginning to the end of the evolution of the calculation. The star actually ends at oxygen, the calculation ends at oxygen burning. You can see that the star started accreting mass at a very high rate. It gets to the equilibrium mass of about 200 solar masses, and then it evolves and actually is able to shed away mass thanks to its super Addington winds, and ends up actually as a 10 solar mass compact Wolf-Rayet star that's going to end up producing likely a black hole. So this is pretty interesting, and the important part here is that this increase in mass is a kind of a runaway process, which due to the fact that bond accretion depend on the square of the mass of the star. So the more mass of the star, the more you want to accrete. Also, the other important point is that the accretion rate depends also on the ratio of the Aegean density to the cube of the sound speed. So once you fix rho and CS, you can determine what your accretion rate is going to be. The mass budget is pretty interesting for the star because the star is accreting and losing mass at the same time. Although it evolves only to 200 solar masses, it loses about 400 solar masses of helium-rich CNO processed material into the Aegean and leaves behind a 10 solar mass black hole. We didn't account for the yields due to the possible supernova explosion. However, already the yields produced by the nuclear processing during the main sequence and later phase of evolution leads to large amount of helium and CNO process elements, like we have several solar mass of oxygen, carbon released into the Aegean. And this can be important for the pollution and evolution in composition. So this is a snapshot of different evolution of different stars at different densities. So this is a log time, as mass of the star as function of log time. As you can see, there are kind of like three groups of stars. There are a group of star low densities that are barely affected. So one solar mass star becomes maybe a few solar mass stars, but you still end up with a low mass object. These are like the circles. The stars symbols show stars that had an evolution similar to the one we just looked at, where it grew to a few hundred solar masses maybe, and then lost most of its mass. It managed evolving till the end of its evolution and dies a compact remnant. And then at very high densities, you can see that there are these stars that seems to reach very high masses, like 1,000 solar masses, and then they keep going for like hundreds of millions of years. So this is like 1,000 solar mass star that live as 1,000 solar mass stars for maybe a giga year. if you let it accrete material as long as it wants. So what is happening there is that the star is well mixed and is accreting at a rate that is higher than the rate that is burning hydrogen in its core. So it's constantly fed fresh fuel from the disk. So pretty much can stay on this main sequence as long as it wants. So it's kind of a idiosyncrasy of this type of evolution. You have the Aegean disk supplying you your nuclear fuel reservoir, and you can stay there as long as you want, despite your luminosity being extremely high. Now, these three types of evolution can be understood pretty easily by the hierarchy of timescale involved in this problem. And so we have the accretion timescale and the nuclear timescale. So if for slow accretion, the accretion timescale is it's larger than nuclear timescale. So the star has time to evolve before it accretes a substantial amount of mass. In the intermediate accretion, you have the accretion timescale is between the nuclear and the Aegean timescale, meaning that the accretion timescale is comparable to the nuclear timescale. So the star is accreting enough mass, but it also has time to evolve past the hydrogen burning during the main sequence. For runaway accretion, the last case of the immortal star, the accretion rate is timescale is much shorter than the nuclear timescale. And so the star stays very massive. So we have this different regime of evolution, and you can turn a 1 solar mass star into this like a 1,000 solar mass behemoth, or you can make a black hole, or you can just like increase its mass a little bit, but still produce a low mass star. So I just want to mention a few next steps we're working on. So the modification to bond accretion. So Alex Dittman has been working on reducing the bond accretion rate by accounting for a few physical processes in Aegean disks that are pretty important, that rely on the fact that you have a disk and a supermassive black hole. So if you have your Bondi radius becoming larger than the pressure, than the scale height in the disk, obviously at some point some rarefication effect's going to increase your accretion rate. Same story if you have a disk, you have a Keplerian flow, so you have shear. So as your Bondi radius become larger, you start accreting material with increasing relative velocity, and so at some point the material won't fall into the black hole anymore. By the way, this is the same reason why, as they accrete, these stars are likely going to increase their angular momentum content. And also because of tides, and this is the most important fact, as you get closer and closer to the black hole, the heliosphere of the star, so it's a gravitational sphere of influence, becomes relatively small, and at some point it becomes smaller than the Bondi radius. So at some point there is material between the Hill radius and the Bondi radius that actually cannot fall onto the star, but is actually captured by the black hole. So these are most important point is that allows to make more realistic map of the outcomes of this Aegean star evolution into disk model. So if you know your sound speed and local and density, you can tell which region I'm gonna accrete at the runaway accretion regime or intermediate, and so you will know which regions form massive and supermassive stars and also compact remnants. And for a disk with constant sound speed, for example, and increasing density moving toward the black hole, you will find that you have this massive stars and the compact remnants and possibly explosion segregated to rings of the disk. Also, Adam is working on this idea that these stars actually might be rapidly spinning. And so checking the angular momentum balance content and how they rotate when they end their lives, he finds that the stars produce compact remnants that are rapidly spinning, and they might be progenitors of relativistic explosion like Long GRB burst. How am I doing with time? Morgan?
I have 5 minutes.
Okay, so next 5 minutes, I'm gonna just talk a little bit about, so these are all interesting theoretical ideas, but is this just fantasy? And obviously we need to look at the observations using this quote from a famous rock band, which by the way has one of the members is actually a PhD in astrophysics. So one place where we believe that it could be useful to look at for looking for signature or effects coming from this type of evolution is the very galactic center of the Milky Way. The reason is that the Milky Way might have experienced an Aegean-like phase about 6 to 7 million years ago. The Fermi bubbles might be showing the effect of that phase. And today we have observation of stellar population and stellar remnants that are directly available. So we can actually explore the inner 1 parsec of the galaxy, which is something we cannot do with Aegeans. And so this galactic center is a pretty wild place. And in fact, within 1 parsec, there are about 200 young massive stars, and which presence is not predicted. And the density of these massive stars increases moving within 1 parsec, and there are actually no massive stars outside of 0.5 parsecs. And the present day mass function is top heavy. Also, some of the stars show like helium enrichment, and you can see here from this. This is from the review of the Galactic Center from Reinhard Genzel, 2010. You can see the population of blue young star confined to the very inner, very 0.5 parsecs in radius of the Galactic Center. The more interesting aspect of this is that if you look at the dynamics of stars in the Galactic Center, the theoretical expectation from Bacall and Wolf is the formation of a cusp. So the density of low mass stars should be increasing as you move toward the galactic center. This shouldn't be the case for massive stars because their lifetime is too short for dynamical relaxation's effect to become important. And yet what you observe is that low mass stars seems to be actually depleted moving into the center of the galaxy, while massive stars seems to be forming sort of stellar cusp. And maybe the idea here, and this is not the only possibility, but what we would suggest using theory is that actually some of the stars, the low mass stars in the galactic center, were turned into more massive stars, and so that's why you see a depletion of a low mass star in the galactic center and increase of more massive object moving toward the inner region. Another piece of the puzzle might be given by the presence of low mass X-ray binaries as identified by Chandra observation, the blue dots in this region, which are confined to the 1 parsec region around the supermassive black hole. So, okay, I wanna just get to the end of this talk by talking about possible implication and prediction. So as I mentioned, population mass and very massive stars in Aegean disk might be common. This might have an impact on the composition evolution of Aegean disk, and also feedback from wind supernovae and GRBs. And a big topic that is discussed this day to explain some of the observation of LIGO-Virgo is the potential hierarchical merger of compact objects in Aegean disk. And here we present a possible way to seed large number of such compact objects in the midplane of Aegean disk. And this might have an impact of, as I mentioned, for galactic center stellar population and abundances. I might not have time to talk to this, but I can answer questions about the possibility of relativistic explosion in Aegean disks. And I want to stop here, and thanks everyone for listening.
Thank you, Matteo.
Thank
you.
So we have a couple questions coming in. If you have questions, what I would ask you to do is private message me in the chat. Not your whole question, just like a couple words is fine about what you have a question about. And you can do that at any time as we're talking. And I will call on you to unmute yourself and ask a question. So as we get started, I think this is a really amazing problem, in part because even if Aegean disks are geometrically thin, we know that they have some aspect ratio, and we know that all supermassive black holes have tons of stars around them, as you said, Matteo, in your cartoon. And so there's a huge fraction of stars that must be undergoing this sort of evolution. Not fraction of stars in the universe as a whole, but fraction of stars in this sort of bizarre and fascinating environment in the first place. So yeah, that's something that I really love about this problem, is that we know that it's happening. And this is a great step towards trying to think about what is happening.
Totally. And I think that the fascinating aspect is really trying to connect it to the observation, and it's tricky because those things are extremely luminous, and most of this evolution might be happening embedded within the disk. However, I think the fact that these stars might become these monsters maybe help us there, because one effect that I think it could be interesting to look for is this idea that maybe the stars producing relativistic explosions embedded in the disk, but depending where they are in the disk, might be actually recognizable. Maybe they've been mistaken as Aegean variability, and maybe nobody ever looked at this problem with the right lens. So I think that this is the type of angle we want to use. And Rosalba is on this call, and she worked on this paper where she tried to map, given a typical Aegean disk models, which I wanna mention. There are all the uncertainties of the case, but assuming that that's a proper model, if you embed one GRB in Aegean disk, depending on the density, obviously your problem is different, and your afterglow or prompt emission might be muffled, and you might see this appearing as a sum of a different type of transient, depending where the transits occur. I found that it's a very fascinating possibility and something we should look at.
And also really interesting to think about these as, we sometimes call these nuclear transients. And so these transients would be spatially coincident with the center of the galaxy as far as we could tell. But they wouldn't necessarily have this high energy sort of pure environment signature that we're so used to.
Yeah, it depends where they are. Some actually will look like very similar to normal GRB, right. And some actually will have part of their, maybe the prompt emission or afterglow being diffused away. And so maybe you might just see the afterglow later on because the early part of the transient was diffused by the fact that you were in a dense environment. So what really matters is the hierarchy of the relevant radii of the problem. So in the fireball internal external shock model, you got the prompt emission that come from the fact that the engine is driving shell of material with different times, but also with different Lorentz factor, and so eventually they hit each other, and you got the gamma rays. And usually that stuff is seen straight away because you're kind of transparent. Your medium outside is transparent. Then later on, the shell hit enough interstellar medium or sequencellar medium in this case, to slow down significantly. You have the external shock that start producing your afterglow. So usually you have this sequence of events, and those radii are hierarchically staggered this way. But in this case, it's funny, you can have so much mass around you that the first thing that happens is an external shock. The first shell goes out, and it finds so much mass around itself that you're ready for an external shock before you make an internal one. So that kind of changes a little bit the laws of afterglows that we're used to. And so Rosalba mapped this type of outcome together with David Lazzati and myself. And I'm not an expert on afterglows. There are definitely people on this call that are better suited to talk about this than I am. But I think it'd be interesting to maybe look at some of these things and trying to find possible signature of this type of explosions.
That's awesome. Well, let's first talk about how stars get there. So Magda, you had a question. Would you like to go ahead?
Yeah. Hi again, Matteo.
Hi, Magda.
Yeah, I had a question about capturing stars into Aegean disks. You mentioned that in the beginning, and I really have an intuition for how easy it is to do that, and especially how easy it is to get the star into the plane of the Aegean disk. It seems like the timescales might be long.
Yeah, it depends how far you are from the center of the galaxy. So this timescale decreases substantially as you get closer and closer. My understanding is that when you're within a parsec, the timescale for capture becomes, a million years or so. So, and there are a number of papers working on this. I mean, the original work on this was from Artemovich from 1993. That's the paper we refer to mostly, but also recently, I think Morgan has worked on this problem. Fabi and collaborators work on this, and it seems to that the result seems to be pretty well understood, that drag and bending waves and spiral waves that you excite in the disk, allow you to capture and grind your orbit into the disk, especially if you're very close to the central region. If you're far out, that might not happen within the lifetime of the Aegean. Remember, those things, as I said, can live up to maybe 100 million years. Some people argue for longer, but let's say conservatively a few million years to 100. So you want to have, so maybe only the very inner regions can do this. Outer regions never manage to trapping stars down. And Morgan, please chime in, since you're the expert here on this type of problem.
Something also that I kind of like about this problem is that process almost certainly takes place, but there's also a guaranteed population of stars that just happen to have orbits that are already within the inclination such that they're within the scale height of the disk already. So even if that didn't take place, this population that Matteo's talking about would exist. Just we're trying to think about like what the relative quantities are.
Yeah, that's a great point. I mean, and this nuclear star cluster, the low mass star lived for a long time. So, they're sitting there spherically around the center, and then an Aegean turns on, whatever direction you're going to intersect this population, as Morgan said, there's going to be some solid angle that's going to be directly embedded into the Aegean disk.
All right, thank you.
So we have another question that I think is a little bit related from Floor. Would you like to go ahead?
I actually now have a different question that might even be more related.
Great. Even better.
So actually, I know, for instance, like Magda works a lot on like binaries of supermassive black holes, and also I think there's a lot of like recent observations that are kind of like showing that, oh, if you actually have two, like say a binary Aegean pair, like two of these black holes, that it actually might help get you things closer to the black hole center, or like the center of the galaxy. So for instance, like with TDEs from the talk from yesterday. So I was wondering if you expect any binarity in Aegeans to have any impact on these results that you showed.
Yeah, that's a good question, Flor. I haven't thought about this much, to be honest. And, I've been starting thinking about Aegeans only maybe a year or two ago. So I'm taking it step by step. And as you well know, similarly to stellar physics, you start with single stars and you go to binaries. I guess here is the same. But it seems like, it might be important into potentially, changing the dynamics of the problem. And I don't know, Morgan, so or someone who's working on the capture problem, or is this gonna have an impact on the dynamics of stars that might be captured or not?
I don't know.
Yeah, it's a good one. I haven't really talked enough about this to have an opinion, actually. Yeah.
Maybe along those lines, Luca, do you want to chime in?
Yeah, actually, also binary question. Thanks for a great talk, by the way. I really love the subject, but more on the stellar binary side. So I was wondering, since it's such a densely populated area in the galactic center, and what fraction of these stars would you expect to form binaries or higher order multiples, and how would that also influence the accretion models that you are with that limit, or change the amount of mass that you expect to be accreted, or in what way actually?
Yeah, no, that's another excellent question, Lika. So we started with a very simple approach where we took like the simple exercise. We put like one solar mass star into Aegean condition and started accreting. Now, if you had a binary system, I think what will happen is that both stars will accrete at some level. Imagine you have a wide binary and material will fall onto the stars and accrete both stars. At some point, I guess one will become more massive and will take it away or run away with respect to the other, and then probably will merge with the other one. That's because the issue is that as the other ones start accreting, you're going to have this stream material falling into the primary in this case, the one that starts becoming the primary. Now the Bondi radius is quite far out, so you might have a situation where the other star, if it's close enough, it's within the Bondi radius of the other one, and now it's kind of like orbiting within a material region which increasingly high density, so it might actually spiral in. You might end up with merging the two stars. Now, if they're far enough that this situation never occurs, like you never enter the Bondi radius of the other one, maybe they can both accrete at some level and evolve and still evolve like separately. But then I don't know what will happen. They will never probably interact. But yeah, I don't know if this will. So I don't think this will change much about the general picture, but it might lead to some interesting effects. I mean, if you manage having two stars, evolving and making, let me think. Yeah, I don't know. I mean, I think that the most important aspect of this comes in with the dynamics later on. And so this is people have been thinking about when you produce compact remnants into this disk, then the important piece of physics is like things like migration and usually the more massive things tend to migrate faster, and then like encounter smaller things. That's the most important effect. So that's how you pair things later on, and how you do this hierarchical merger. And so you don't really need to form compact remnants close to each other in the first place to be competitive for like producing gravitational wave sources. That's where you're going. But it might be that in some case you might directly form two compact remnants orbiting each other in the first place. So it's not very. It's again, I'm brainstorming as I'm speaking. It's not something I thought extensively about. But yeah, we can discuss more offline about this because I think it's a good idea.
Yeah, no, thanks. I was actually also wondering because there's this whole discussion going on whether or not stars will widen or shrink if you have a circumbinary accretion. But you're right. Let's maybe do this offline. But thank you.
No, but this is wonderful, and it's exciting to have work that is at all different stages, and is exciting when a discussion can actually feed into what research happens next. So I think that's great, not a shortcoming. So I'm wondering if we can talk a little bit more about essentially the boundary conditions of the disk properties at a given location and how they influence what happens. So it seems to me that like the far in disk conditions, which are optically thick and very dense, might be very different from like an optically thin, lower relative density, like surface density compared to the star. And so with that kind of in mind, I think Martin, Elvis has a related question. So maybe you can go ahead, Martin, and then we can let Matteo.
Oh, hi. Yeah, I was trying to relate your diagrams to the scales that we know happen in Aegean, like where the UV continuum comes from, where the broadline region is formed, and that's over quite a range, where the torus is. And I couldn't really get a feel for that. Do we scale things to a Schwarzschild radii in this picture? Or?
Yeah, Martin, thanks. So the reason why I didn't put any physical scaling there is that the outcome relies on the disk model that one used, and we haven't yet done, and this is something that we're working on as we speak. So as I mentioned, like Alexander Dittmann is working on getting better grasp of the density limit and sound speed limit where we expect certain type of stellar evolution to occur. And so that maps to if you map it that once with that in mind to a disk model, then you can tell, okay, within this model, for example, within the Circo and Goodman model, we get massive stars in the range of like 0.1 to 1 parsec. So, and before we can put numbers like that, we need to do the final pass of projecting our prediction onto a disk model. That's something we haven't done yet because, well, the first paper we put out, we only account for Bondi accretion. That is, we pretty much put a star in the box. But as I mentioned, this is not a box, it's an Aegean disk, and there are other effects. For example, one thing that we didn't account in the first paper is that if you get closer and closer to the black hole, the density goes up. It's true. So in theory, your accretion goes up, but actually your boundary radius is not the relevant radius anymore. Your Hill radius becomes a relevant quantity. And actually that shrinks as you get closer. So you got this counterintuitive effect that as you move closer at some point, you're not making massive stars anymore. You actually accrete very low. So the prediction is that we're going to have this kind of rings and the boundary of this ring will depend on the disk model and on this prediction that are in Alex's paper. Now, the other thing that is important to remember, that's something that I mentioned briefly, is that those models of Aegean disk are built without the effects of these stars. Now, if you have these stars embedded into this disk, now the expectation is there's going to be some extra heating and some extra energy sources. So your Q plus term into this model needs to be accounted for. So we will have to do that as well, I think, eventually. So this model will have to be built self-consistently with the fact that those stars exist. So there are a few steps between us being able to firmly say, okay, you expect this evolution to occur between, say, 0.5 and 1 parsec for a supermassive black hole of this size. But that's where we want to go. So your question is absolutely on point, Martin. And unfortunately, I cannot tell you yet what's the I can only give this cartoons where we can give an hierarchy, but we cannot put yet numbers.
And I guess the density of stars in the disk is going to feed back into the disk model if there's an energy input from them and so on. So it gets multidimensional.
Right. So that's again, so the density of stars, it's also a question. It's important. So on one hand, we can sort of predict what the capture rate is. So, if we know the typical density of a neutron star cluster, we can tell, depending where you're in the disk, how many stars you can capture. As we discussed earlier, the closer you get, the more stars you get. You go outside, you get lower number of stars. But the other elephant in the room is the fact that the disk can form stars themselves. And now predicting how many of these stars can be formed, again, it depends on the disk model. So there's a little bit of this complicated feedback loop that one has to take into consideration. So I think it's going to take some time, but we have the tools, I think, to build that knowledge. And I think this, again, as I mentioned earlier, this is a problem that require different angle and different expertises. And so, it's a cross-disciplinary problem, but I'm accreting smart people that are know much more than I do. So I'm confident.
Great talk, by the way.
Thank you.
Okay, so if we continue with accretion, maybe Ramesh, would you like to go ahead?
Yeah, I was wondering, once the star has been captured by the disk, I imagine that it will also try to migrate radially. And you must have estimated the time scale for that. So how does that time scale compare with the other time scales in your problem? 100 million years is a long time.
Yeah, no, it's an excellent question. I must confess, I haven't calculated that time scale because in this first paper, we really said, okay, let's not deal with the dynamics yet. It is true that the more massive the star become, also the more likely it's going to migrate. And so that process will be important. Migration in the disk is actually complicated, and there's a lot of work happening on trying to understand how this process work. And migration can actually go both ways. You can have inward migration and outward migration depending on different physical processes that you account for. But I think again, next steps will also have to pair the style evolution with the dynamics, which it's right now, our accretion rate is fixed, but if you have a model for the dynamics, for example, what's the time scale for your migration, which direction you're going, then you can, and you have a model for an Aegean model, you can also change the accretion rate dynamically as you move through the disk, and that will tell you, for example, what the outcome for that star. We're not there yet.
Razi, would you like to go ahead?
Hi, very fascinating talk. So I have a question regarding to possible hydrodynamical effects. Have you thought of it in your accretion disk, more specifically about like the gas cooling or like newly born stars at different actually parts of the disk? And also something that might be related about the thickness of your accretion disk. Is this going to be a static or throughout this kind of like, complex process entirely, can it just like get like thicker and thinner, and so thank you. Yeah.
Okay, so concerning the second part of the question, so like the disk model, so currently what we do is we assume, so the first step we did is that we assume that the accretion pretty much is constant, so we put the star in a box, so to speak, and that box corresponds to local condition in Aegean disk. The second order approximation was including the effect of rarification. So given the scale height, local scale height of the disk, we say, okay, we had a disk model, and as your boundary radius increase, because your mass of the star increase, you're capturing region of the disk that increasingly have lower density, and because of rarification effect. And so you include that effect. Now, we haven't projected again this on a realistic disk model where your scale height might fluctuate, as you correctly said, and that's something that we'll have to do once we, going back to Martin's question, we want to get realistic predictions for the location on the disk where a certain type of Aegean star evolution occur. So yeah, so that's the I think this problem, since it's there's so many moving parts, the approach has been starting with the simplest possible experiment and then adding level of complexities. And we already found that that's already a lot to chew.
Yeah, very nice. And about the gas cooling, actually, have you maybe already said, but do you also consider the, like not put the stars there, but just like newly born stars actually throughout the evolution of the system? Do you also consider that somehow? Or?
Yeah, right. So eventually, once we have like feedback into the disk model, we'll have to account for both effect of heating and cooling due to the star formation and evolution and the possibility of having explosions, things like that. Currently, that feedback is not included in the sense that the star doesn't know about the Aegean, in the sense it doesn't know about the Aegean beside the initial density and sound speed that we tell the star to accrete at. But as you said, eventually a perfect model of this will be a model where the star knows about the Aegean disk model and the Aegean disk model knows about the star at the same time, and there is crosstalk. So that I envision that with something maybe we can do in the future, but not immediately.
Okay, sorry, and the final actually things related. When you're talking that stars doesn't know about the accretion disk and vice versa, I was wondering about the accretion rate that you said. Could it also depend on metallicity? Because you just consider m² rho over c actually cube, but I can imagine that just like different process, different actually a stage of the accretion could also depend on your stellar metallicity, but maybe I'm wrong actually. I know.
No, actually, this is a good point. I think I haven't touched much on the metallicity effect, but that's an important one. So the accretion onto the star, it's going to depend on the metallicity, if anything, because as I mentioned, those stars accrete rapidly. Initially, they're low mass, and they accrete and become massive star. And as I mentioned, they start this accretion. This process is either halted or stalls when the star hits the light into luminosity. This is the point where the radiation acceleration from the luminosity of the star becomes comparable to gravity, and so the other layers become like not unbound. In that case, the point where this happens depends on the metallicity, because the Eddington luminosity depends on the opacity of the star, and the opacity depends strictly on the metallicity. So, the more metal rich you are when you go out in the other regions of the star, the higher the opacity it is. And so in a sense that decreases the maximum mass of the star you can form. So the prediction, I think, is, and we haven't studied this in detail, but the qualitative prediction is that if you increase the metallicity of the gas that you're accreting, so if you increase the metallicity of the Aegean, and again, this is something that the Aegean will know if he knows how many massive stars you're producing. So that's something that the star also dictate. But let's say if you increase the metallicity of the Aegean disk, the material that falls in has higher metallicity, so the maximum mass of the star that you can reach decreases because your Eddington luminosity decreases. So I think that that's another prediction of this type of evolution. You're still gonna make massive stars, and you're still gonna make compact remnants. So I think that qualitatively doesn't change, but it might change, for example, the heating, because now all your stars, the most massive stars you produce are not 1,000 solar mass anymore. Maybe they're a few hundred or 100.
Thank you.
So Matteo has a kind of last word. What do you think that something that we've learned is that this problem is going to rely a lot on the subtleties of what the disk properties are at a certain radius, or maybe even it's the case that there is a whole spectrum of different outcomes contained within a single accretion disk. So given that range of possibilities, what do you think are the observations that will be most determinant or most distinguishing to convince us that we're understanding the sort of physics that's going on in this sort of relatively enshrouded environment?
Yeah, outside of the galactic center, which I think it's probably our best bet initially for trying to look at the remnant of like maybe an Aegean disk phase, and looking at the radial stratification of stellar population and their abundances. Because one thing that it's important is that now imagine you have this Aegean disk which is on for a while in the galactic center. Some of the stars that we talk about do their shenanigans and enrich the disk. And if the disk is well mixed, so the material that is processed in the regions might end up in other regions where the accretion is lower. So now you can have a 1 solar mass star that is in the other part of the disk. It's accreting maybe a solid mass of processed material in the disk, and then the disk disappears. You're in this slow regime of accretion. And so those stars might still be around. It's a 2 solar mass star, at least for a really long time. And maybe it adds at the surface the memory of some composition of the disk. So I think that spectroscopy of the galactic center and better understanding of the dynamics of the stellar population, it's an important aspect of this problem in terms of grounding this with observation. And the other direction, I think, is, LIGO is an interesting one. It's very indirect, I think. It's not going to tell us much about, there are many ways to do things in Aegean disk. You don't necessarily require this type of evolution, but maybe the rates will tell us something about this. And then the other direction I think it's currently seems promising is this idea of relativistic explosions in the disks. And I think if you see one of these muffled GRBs that Rosalba predicted, I think, that will tell you that some of the stars are actually, doing this in this Aegean disk. Maybe it won't tell you exactly where in the disk, but maybe by correlating this with the mass of the galaxy, and so the mass of the supermassive black hole, maybe you can learn something about the Aegean evolution.
That's really wonderful. Well, everyone join me in thanking Matteo again. Thank you all for being here. Thank you, Matteo. This has been a really wonderful discussion. We're really grateful.
No, thank you guys, and thanks for giving me the time. And I have to say, this is a very exciting discussion. I never had this many good questions at the talk, so I really like this format, despite the fact that I had to cut down my presentation by half.
That's right. We give you at least 5 minutes.
But I think it worked because we were able to discuss all the things that I wanted to via questions. So that's perfect.
I'm glad to hear that.